folks, today we are going to talk about something truly transformative: connecting the world through space. Okay, more specifically, low Earth orbit or LEO satellites. Over the last few years, LEO constellations have moved from an ambitious concept to crucial reality, fundamentally changing global communication, internet access, and data transfer. And these systems rely on high performance, compact, and highly reliable RF technology to function. Folks, we've got miles to cover, so we best get started. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Ryan Jennings from Qorvo and I explore the critical components and design challenges inherent in LEO satellite infrastructure, from the ground station to the user terminal, and how Qorvo's solutions are enabling the next generation of space-based connectivity. And before we get started, don't forget to click that link. There you can find even more information about this topic from Qorvo. Hi, Ryan. Thank you so much for joining me.
Thanks for having me today, Amelia.
Absolutely. All right, Ryan. So we're talking all about the satellite ecosystem today. So, to start things off, give us a review of LEO satellites and the benefits that they bring to global communication.
Yeah, historically, we've used geo satellites for all of our communications, and they were very, large, expensive satellites, had long lifespans, so high reliability, required many years to build and deploy. And that was the mainstay of satellite connectivity for many, many decades. That came with, limitations on coverage and performance. Whereas the new LEO constellations that we have now, they're much closer to the Earth, so very low propagation delays makes them very useful for voice communication. So when you're doing, video teleconferencing, it actually is useful for that kind of applications. Whereas GEO had such a lag due to the propagation delays, it was problematic. They also provide much higher capacity on a specific point on the Earth, given that the coverage is much smaller footprint. All the capacity of that satellite can be focused into that very much smaller footprint. Now, it does require multiple satellites to get the full Earth coverage, which historically has been a downside. But with the low cost launch capabilities that have been brought, where they're, Starlink, as an example, puts up 70 some odd satellites every time they shoot up a rocket versus a geo satellite was one. That scale has really enabled this market to be viable. And we see that with a number of constellations that are there today and multiple that are planned for the future, providing this high data rate connectivity, not small data rate stuff, but very high data rate stuff. And we see this new LEO ecosystem supporting a large variety of applications. National security is one of those that we see that has driven a lot of it, but from direct to device handset stuff that we'll talk about, home consumer, commercial activities, to, military, all the way to the next generation fighter jets, all want this type of connectivity that the LEO constellations really enable to provide huge data throughputs and connect everybody in the world. As I mentioned, that, the growing ecosystem of LEO satellites with Starlink, Amazon Kuiper, OneWeb, Telesat, Bravada, SDA. This is just a small group of those. There's many across the globe that are being planned, some that have already started their launch cycles. So it's an exciting time in this LEO satellite ecosystem.
So, Ryan, what do you think are the biggest challenges within the LEO SATCOM architecture and ecosystem?
So, as I mentioned, the footprint coverage on Earth of any single satellite is very small. So, in order to provide service, you have to launch a bunch of satellites to get the coverage that you need before you can ever have your day one of service capability. And so, it's a big upfront commitment for these operators to launch these satellites and get sufficient so that they can actually start economizing them. That's one of the really big concerns. And, 2 decades ago, people were like, well, you'll never make this economically viable. But we now see that that is possible. As I mentioned, one of the key things is launch cost is a fraction of what it used to be today. So the number of companies that are able to offer that continue to grow on a yearly basis. So with the Leo architectures, the ecosystem is very unique for the different functions that are provided as part of that. Looking on the far left side, we mentioned, low data rate applications for direct to device, whether it be, direct to your cell phone or to a small Internet of Things device. That's one piece of the market that is a recent growth area. You have the traditional high data rate user terminals, whether that's the consumer thing that you mount at your house, all the way to the defense side of things. And then in order for those satellites to get that data back to the rest of the world, they use gateways to connect back to Earth stations that provide that link back basically to the internet backbone. And so as we look at some more of these challenges on the space side with this volume of LEO satellites that you have to put up, what is a sufficient qualification that meets the reliability needs? When we talk about GEOs, it was a very rigid, this has to last for 20 years, whereas now it's these satellites are 5 to 7 years. So coming to an agreement on the requirements for qualification is very different between the risk profiles of constellation to constellation. But all of them continue to have thermal performance, it being one of the key drivers there. In space, you don't have air that like we breathe to help radiate the heat. Additionally, the efficiency for DC power, which is also a driver in your thermal, but also drives the spacecraft's needs for power to run these systems, is extremely important as well. When we look at the gateways, thermal performance is also a driver, as well as the DC efficiencies. You'll have multiple of these ground stations typically in a single location to connect to all of the LEO satellites that are in the field of view. So the simultaneous connectivity drives the need for lower power, better efficiency, and importantly, lower cost, because since there's so many of those in the system. For the user terminals, again, thermal performance comes up. That's going to be a common theme between all of these areas, as well as DC efficiency, which drives the thermal performance, but also cost. And this is very, very important. When you look at what you're going to deploy to a consumer terminal at your home, needs to be super, super low cost in order to make that viable to compare against other high data rate services that are available in some of the areas where this is useful. And then lastly, the low data rate applications. So your receive sensitivity is super important. You're trying to talk from space to something in your hand. That's much more complex requirement than talking to a larger antenna that would be your high data rate. Those handsets also talk to things on the ground in the similar frequencies or the exact frequencies. So how you manage that frequency reuse is very complex and still, I think, not quite resolved in the industry yet. And then just the drive for these low cost COTS or custom IoT devices that are very low cost are some unique challenges that we don't see today in the traditional high throughput market.
All right. So, Ryan, considering all of the challenges you just mentioned, what kind of questions should we be asking ourselves as we move forward with direct to device applications?
Yeah, so as we look at specifically the breakdown of the space market, direct to device is obviously one of those. Gateways and the high throughput links are all on the satellite. So as you see from the picture, is an example of a Starlink satellite where it is marked the gateways and the high throughput data links, and then an AST mobile phased array solution for space that is doing the direct to device. I think specifically for direct to device, the viability of the business case is still kind of up in the air. It's cost a lot of money to put these things here. As I mentioned, in many of these applications, their desire to reuse the same frequencies that you use in the ground-based cellular network. And how do you manage not interfering with those while being able to use the space side to fill in the gaps where you may not have good coverage from ground locations? And this is a regulatory thing that is still somewhat in flux. So it'll be interesting to see over the next 6 to 9 months where all this lands out. Thinking forward, I mentioned the radiation testing is something that we as Qorvo are trying to come up with some standards to make it more efficient and effective for these operators. For the direct to device specifically, how many different people can do this and make money off of it? It seems like there's constantly a new player that wants to provide this kind of capability, whether it's, direct to a cell phone is probably the dominant piece of this, but also direct to other devices to provide a variety of different services that don't require significant data rates. And I think one of the last things of great interest to the future is what are the new frequency bands outside of the traditional KU and KA bands are going to be made available and successfully deployed for the high throughput side of the links. As we continue to have more constellations go up, there's still limited frequencies at those KU and KA bands that have to be shared, not only within the LEO operators, but they're also used in the GEO as well. So you have to ensure that you're not interfering with each other, which is a very complex problem, particularly when you have, hundreds to thousands of satellites in orbit.
So, Ryan, can we dig in a little deeper into these kinds of applications?
Absolutely. Let's take a look at direct to device first. So those are typically done at L, S, and C bands, so lower frequencies. The satellite side uses large phased arrays, typically for this application, that are multi beams, much like the picture on the previous slide for the AST mobile solution. And they're all using, digital beamformers because of this very high beam count. And so Qorvo does provide a number of components supporting this architecture that can enable this capability. Here's an example block diagram. There's a lot of variations potential to this, but this gives you a kind of a high level picture of what could be done. The components that we can provide, like the high power amplifiers for all of those bands, gain stages for those, the LNA for the front end, step attenuators, mixers, and LO drivers. So all of these different components are needed to build the front ends that go prior to the digital beamforming for these applications. And filtering is another very important piece of it to minimize your loss, but maximizing the isolation between the different bands that are used in these applications.
So, what about the gateways you mentioned earlier? Can we talk about those a bit more?
Absolutely. So for the gateways, there's a couple of different applications. One is telemetry tracking control. So that's typically below C band in frequency and is what they use to monitor, manage, and control the spacecraft bus versus the payload data, which is potentially very large data throughput requirements. And those are typically done at Ka and Q bands. There's some satellites, typically the Earth observation kind of things, may do it at X band, but today Ka and Q bands are the primary bands. And on the satellites, as shown in the previous picture for Starlink, they're typically mechanically steered horns or reflectors. However, phased arrays are coming, and typically starting with analog beamforming, you just need to talk to one ground station at a time. And on that previous slide, there was a picture showing a product that's in the market today that people are using for that application. And Qorvo has components that can enable multiple architectures. Again, a similar example, front end architecture for this type of application, where we have high power amplifiers, gain stages, the front end LNA, phase shifters, mixers, and gain stages.
So, Ryan, can you also talk a bit about the high throughput links as well?
Absolutely. So, as I mentioned today, those are typically at KU and KA bands with potentially future bands coming. All of these platforms are basically using phased array antennas, and it really comes down to you want a lot of beams pointed from each satellite so that you can reuse frequency and provide the maximum amount of data throughput. So digital beamforming is the route for that. But we have a lot of components that support the front end prior to that digital beamforming. Here's an example block diagram. Again, there's variations to this, but typically you have separate transmit and receive apertures, and that photograph shown of Starlink as an example of how they do that. But we provide the high power amplifiers on the transmit side and gain stages for both transmit and receive sides of the link.
Okay, so Ryan, earlier you mentioned Earth stations. So, can we also take a closer look at that element as well?
Absolutely. Yeah. So switching to the ground side of things, we look at the Earth station that would be your gateway connecting the satellite back to the back end of the internet. These are typically done with reflectors today where you have, medium sized to large dishes depending on the application, separate power amplifier blocks and low noise amplifier blocks. And as I mentioned, at a typical LEO ground station, you're going to have multiple reflectors to connect to all the satellites that are above them. So there is a desire to consolidate that to a multi-beam phased array, but to date, cost has been a limitation there. So while people are working on that technology, it isn't quite there yet from that cost perspective. Technically, it's certainly viable. One of the things that we see as a challenge going forward, many of these satellites are interconnected via laser cross links so that they can use all the satellites to network together and downlink that data at specific locations on the Earth and minimize the number of those ground stations that they need because they don't necessarily have to be under the footprint of a specific satellite if you can bounce the signal out in space before you take it down. But in order to do that, you have to have much higher throughputs because you're adding all the data from multiple satellites and pushing them down to a consolidated ground station. So higher frequencies provide higher bandwidths. So there's a lot of work going on now to increase that frequency to enable much higher throughputs through the next generation LEO satellites that are coming out. And this is things that are above 30 gigahertz to be able to achieve that. Also, as I mentioned, this arrays versus traditional reflectors. There's some photos here showing some concepts and some real hardware where people have done this. Again, it's about driving the cost down before we can very widely deploy this type of solution.
So, Ryan, what do you think are the biggest challenges with these Earth stations?
As I mentioned, the reflectors versus multi beam arrays, as we get more and more satellites, the number of reflectors that you need exponentially starts to grow at each of these locations. So having something that can not only, minimize the footprint, but removes the mechanical failure rates that you might see with a reflector, as well as the cost associated with just buying more and more and more reflectors. So I definitely see a big challenge to get the cost out of these arrays for long-term solutions to do these multi-beam solutions to connect with multiple satellites simultaneously.
So, Ryan, talk to me a bit more about those reflectors you mentioned.
Yeah, so we talked on the spacecraft side about the telemetry tracking control. So those are things that are below C band, whereas the payload data is Ka and Q bands. And as I mentioned, historically, this has been done with mechanically steered reflectors or dishes. And at Qorvo, we do provide a lot of components that are used in these architectures today using this similar basic block diagram. The front end high power amplifiers, the gain stages to drive those, the LNAs, step attenuators, phase shifters, mixers, LO driver stages are all components that we support in these different frequency bands and architectures.
All right. So, what about those gateway arrays? Can you address those a bit more as well?
Absolutely. So we're seeing those arrays starting to enter the market, as I mentioned, using analog beamformers, given the power draws and capabilities of technology today. They're primarily, we're seeing today at Ka band, some higher frequencies for increased bandwidth, but typically get Ka band. And again, requiring multiple simultaneous beams to connect to the satellites overhead and bring that data back to Earth. You're typically using either whether it's multiple beamformers or multiple channel beamformers. And again, at Qorvo, we have components to support this. You look at a basic diagram where we have multiple beamformers for typically every quad element in a solution. And then as you do the corporate combining of all of those signals from each individual antenna element in the phased array, we have the gain stages to support combining all that to get to a single output to drive the modem.
So, Ryan, I believe you also mentioned user terminal applications earlier as well. Is that correct?
Yes, that is correct. And so if you look at that market, consumer, enterprise, backhaul, airborne, maritime, land mobility, defense, it covers all kinds of applications with even within those sectors. And as part of what we see in that ecosystem, I mentioned earlier, DC power is very important. You typically don't want to have active cooling solutions, so a passive, and that's always a challenge with these multi-element phased arrays that are used in these architectures. And cost. Cost is king for all of this. As the architecture of a phased array requires multiple beamformer ICs, they really can dominate the terminal cost. And that's an area that Qorvo particularly we're focused on to be able to enable more capabilities at a lower cost and lower power. Looking forward in that, there's a big race for low cost, but with good performance. And I say good performance because we can't get the absolute best ever possible in the best technology because the cost is prohibitive there. That's one of the big differences that we've seen historically from, the defense world where you want to eke out every tenth of a dB, whereas this is what's good enough for the right price. A lot of these operators are doing their own consumer terminals, and some of the verticals that I mentioned outside of that consumer, but there's always options and need for people outside of the operators to provide solutions, whether that's for multi orbits, multi constellations. But one of the future things that we really believe in is dual band. So the ability to have a single antenna that operates at either Ku or Ka band and can support any of the orbits, whether it's LEO, MEO, GEO. You look at that as kind of the iPhone of an antenna, and there's lots of value for many applications. I'll use airborne as an example of that, where it costs a lot of money to put an antenna on an aircraft and get all the certifications required. And if you put a antenna that's custom to a single constellation, that gives you little ability to change in the future if a better solution comes down the pike or that solution gets oversubscribed to. So having a universal antenna actually puts the power back in the user, much like you have with your cell phone, where you can change a carrier at any time that you want to get the best value to provide to your customer in whatever application that you're using. And we do see in the market some requests for dual beam, which would allow you to receive from two satellites at the same time, but that's not universally supported or needed, and it's definitely more costly. And I'll use an example of before the LEO satellites were deployed, we all thought you had to do a make before break to hand off from one satellite to the next to ensure data throughput. But now that it's actually in place, we've learned that the electronically steered antennas can switch very quickly in a IP-based network that is really unnoticeable to the end users. So adding that second beam adds a lot of cost. And because you can actually do that switching very quickly, the constellation operators don't want to support dual make before break dual beam requirements because it just pulls resources from their network that's unnecessary.
That makes sense. Now, when it comes to high throughput arrays, what should we keep in mind for the future? What kind of challenges are we going to face?
Yes, so obviously cost is a big piece of that. And as I mentioned, the dual band desire to be able to have this universal capability, those are two very important things I see for the future. Being able to provide that technology at a cost effective price point and at a thermal load that is usable by the masses of applications, not just, very particular high end applications. So as we look at the high throughput array architectures for the grounds, today they're typically at KUKA bands. We're excited about the potential for future other bands, but it is dominated by phased arrays. to support the dynamics required from LEO networks, so that fast switching that I mentioned, but also multi-orbit solutions where you could point to a geo satellite or a MEO satellite when that's most valued to the customer, or switch to a LEO satellite where that provides the best coverage. And we're seeing a lot of things working in this LEO, MEO, geo networks for government, but also pushing into the commercial market. As I mentioned, single beam is typically what is needed for the majority of these applications. As Qorvo, we have a large variety of products to support these types of architectures where you have the front end beamformers that support typically 4 elements. All of those signals are combined together using binding networks that have active gain stages that then combine to a single output that could connect into the modem solutions.
All right. So, what about applications with a low data rate? How do they fit in here?
Yeah, so looking at the handset and IoT in the LEO architecture, you need to be on a LEO satellite in order to provide enough signal to connect to these small devices. And the fact that there's a bunch of those LEO satellites going up today, it's easy to add this capability to some of those satellites in addition to the high data rate in order to provide additional services with minimal increases in launch and operation costs. So we look at some of these challenges, the high cost to launch. And when I say that, when you compare the number of bits that you can provide at these low data rates versus the number of bits that you provide for the high data rate, that really increases the launch costs relative to a bit rate. The complexities of this market are pretty high, given that, like the direct to cell, as I mentioned, you have to manage frequency spectrum and power levels. And how do you make devices work with obstructions, which requires more power, versus the non-cellular device market where maybe you have an IoT thing that goes in your car that allows the car manufacturers to pull data from your car to do preventive maintenance or software updates, versus having tracking devices that can go into shipping organizations. There's just a lot of different capabilities there, but the market is a little bit untapped, undefined on what are people willing to pay for that. So that's one of the big challenges moving forward for these types of applications.
So, when it comes to these kinds of applications, what kind of challenges are we looking at?
Yeah, so I think the biggest thing that I've already discussed is the cost. And are people willing to pay enough for these types of services such that you can actually make a business case where you make money, which is what all of these guys are looking for today. It's a market that is still emerging. We've kind of got one of those things where we're bringing the technology first and then seeing, how many people we can get to sign up. That's going to be the biggest challenge. Can we really make this a viable market? And how many people can provide these services in that market?
That makes sense. So, Ryan, before we go, is there anything you'd like my audience to take away from today's Chalk Talk?
I think one of the key things, as you can see, is the ecosystem is very complex and it is very diverse. We oftentimes think about, I can go buy a Starlink or a OneWeb terminal that's small, put it on my house or my boat. But there's a lot on the back end that goes into making all of this function. It's a very complex ecosystem. And as Qorvo being a wireless company, we are very focused on supporting all aspects of this market. So if there are challenges that our customers have, we're happy to engage more on where we can bring our technology to enable these markets to be successful.
Fantastic. Well, Ryan, I think that's all I have time for today. Thank you so much for joining me.
Thanks again for having me.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Qorvo. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com slash EE Journal.